Okay, so welcome back. We will now talk about this SAT attack on logic locking. So, what we have seen so far is it is good to lock at the higher abstraction level, which will give you more protections, in the sense you can actually lock the semantic information, but most of the work try to lock in the gate level, and we have went through 3 of the such techniques, right, which is essentially putting XOR XNOR gates in the design and such a way that it is not easy to guess the key, right. And normal brute force method is that you try for key value 0 and check whether the output is matching with the inputs. If it is not, then you try for the key value next value and so on, right. It is a brute force and it will take exponential algorithm. And as I mentioned that obviously this exponential is not going to work even if the k size is 50-60, right, 2 to the power 50 is not breakable. But there are smarter people in the world, so they come up with some technique called SAT attack, right. So, what they effectively does, they use formal methods, right, satisfiability checker, right. So, you know what is satisfiability checker? Professor Mishra introduced that verification technique, right. So, what this satisfiability solver does is, if you give a formula, Boolean formula, okay. So, if you give a Boolean formula, right. So, it may be something like this, A and B or C and not D and so on, right, something like this, some big formula. This tool will tell you, does there exist a value to the inputs that ABC, in this example ABCD, for which this formula will become true. Okay. So, it will basically return if it is there. So, it will say for example, in this case, if B is equal to 1 and say C equal to 0, this will be true, and say A equal to 1, right. So, if you have this, so A must be 1, say B is 1, this is 1, and then say D equal to 0, right. So, it is basically A equal to 1, B equal to 1, C equal to 0, C equal to 0 and D equal to 0. So, for this values, this formula is true, right. The SAT attack tool, SAT solvers is forget I differentiate between two. This is a SAT solver, right. It is a formal verification technique again, right, and it has been used widely in verification, right. You try to check whether through circuits are equivalent, whether many things you can check, right. But the core idea is that in the SAT solver, you need to give a formula, and this particular tool will tell you if the formula can have an input for which the formula is true, it will return you that value, okay, and it will say SAT or satisfiable, and it will give you the example or the values for which the formula is true. Okay. So, what attacker does is they try to use this SAT solver to attack that lock design, right. So, in the lock design you have the keys and they mount the attack such a way the satisfiability means the key, right. So, I will talk about that. So, the satisfiability will help you to prune out the wrong keys quickly and finally, you will get the correct key. Okay. So, that is the core idea between this SAT attack on logic locking. Okay. So, let us go into more detail. So, everybody understand what is SAT solvers, because you need to know that, right, and what is SAT attack kind of, understood. So, I will go into more detail on how things works. Okay. So, in any this security domain, the first thing is the attack model or the adversary model. So, what are the things attacker can have, that let us list out. Okay. So, the attacker can reverse engineer the netlist, right. So, you have the layout and I have already shown you the reverse engineering process, and they will get a locked net level design. Okay. So, they will basically get this structure. Okay. It is possible because you have the layout, from there you reverse engineer, you basically get this. So, you get this circuit, you can run it basically, only thing is that you do not know the key values. Okay. So, attacker has that capability. Okay. And between the inputs, he also kind of knows what are the input is actual input and what are the input is key input. Okay. So, that is the second thing, distinguish between the key inputs and the regular inputs. It is possible, right? Some trial and error he can make out, oh, these are the ABC and this is K1, K2. So, that they can do. Okay. And this is I have already talked about, reverse engineer a get level netlist from the that layout, but this is the locked one, right, the locked netlist. Okay. And he can actually do some further analysis, because he get the circuit, he can do all the SAT analysis and all, because he can model the circuit as a SAT formula. The most important thing is this. So, you as a company, you build the chip, you put that key in a tamper proof memory and you are selling this in the market, right. So, this is your IC, right. These are the keys, this comes from a tamper proof memory, this as a whole you are selling into the market, right, which has input and output. So, this is called Oracle or functional IP. Okay. Okay. So, you make this chip and sell into the market and attacker buy one of them, right. He can also be a customer of your company, he purchase one such thing, which is called Oracle or functional IP. He can do that, right. So, he can has that, but what is this can be used for? Again he cannot break it, right. So, this is basically packaged together. So, he can only give some input and know what is the correct output, that he can do. For the circuit, what is the, for one input, what is the correct output, he can make out by just running that input into this Oracle. Agreed? This is possible, right. Any question on this, the attack model? Does there any questions on any of the things that attacker cannot have? He can, right. So, all these 4 points that I talked about, that he can distinguish between key input and regular inputs, reverse engineer the netlist, get level netlist, he can do further analysis like SAT, and he can buy the activated IC, this is called activated IC market, and observe the input output patterns. Okay. With this he want to break your design, want to get the correct key values. Okay. There are different kind of attack possible, one is the active adversary and the passive adversary. So, the difference only whether you have the activated IC available or not, right. Rest 3 are common to both. In active model you assume that you can purchase that IP from the market, and in passive model you do not have that, you do not know what is the correct output also. So, this is much difficult attack, right, because you do not know for an input what is the correct output, but in this case you have all these 3 plus the IP, the Oracle. Okay. So, there are many attacks has been developed. In today's class I will mostly talk about SAT attack and what kind of AI techniques can be used to identify the keys also. So, there are some recent work that try to use machine learning techniques to get the key. So, I will talk about those also. Okay. So, if you classify them, one is structural attack, which is basically once you apply this XNOR gate and XOR gate and you do the bubble pushing, they actually make a small modification in the locally, it is not the entire circuit, right, and the possible of changes is limited. So, the structural attack what it does, it try to see what are the possible changes, right. If there is a AND gate and if you do a bubble pushing, what is the changes? If there is a XOR gate, there is a bubble pushing, what is the changes? And this bubble you push only either one level or two level, right. So, if it is push one level, what will be the possible circuits? So, from this analysis you can do something, right. So, that is something structural attack, and even machine learning try to do the similar stuff. And functional attack is basically the SAT or BDD based attack, which is basically assume the it does not see the structure, it take the entire circuit as a whole and try to do the attack. Okay. And it has two kind of active and passive, whether you assume that whether that Oracle is available or not, based on that you can classify into active and passive. Any question here? So, there are many ways you can do attack. right. So, we will speak some of them. So, now let us move on to the attack. So, once you have this circuit with you, okay. So, the key value for this, so you have two keys, right, K1 and K2, and let us assume, because I have not do that bubble pushing and also the actual key value is 0 0, right. So, I just want to demonstrate that things is happening. Okay. So, what attacker will do, right. So, if you give any input, right. So, this circuit, if you give any input here, you can give, basically this is a locked design, but you can give any input, right. So, you give 0 1 1, right, you will get some output, right, you will get some output, and the key value can be, you can assume something. Okay. So, now if you think, see here, if you give say 0 1 1, okay, what will happen, because this is a AND gate. So, this will become 0, this is coming here. So, this will become 0, and this is basically B and C, this will be 1, and since this is a OR gate, it does not matter what is coming here, because this is 1. So, this will be always 1, right. So, in this case, even if you give any value of K1 and K2, your output will be 1. Okay. So, what attacker found, that this kind of inputs are useless, because they are not distinguishing the keys, whether this keys is correct or incorrect, I do not care, right. So, in this case 0 1 1, your output will be always 1, immaterial what is the value of K1 K2, and that will be corresponding to the correct output also, right, because this is OR gate, one of the input is 1. So, it will be always 1, right. So, sum of the input is not so important for the attacker, understood, just like your 0 1 1 or 1 1 1, because if you give 1 1 also, this will be 1 and output will be 1. I want some input which is distinguishing input, right. They can separate some key as correct key, some key as wrong key, they can separate them. Okay. Let us see. So, let us now see this this key, right, 0 0 0. If you give 0 0 0, because this is 0, so this particular gate has no impact, right. So, this will be 0 and this is also 0. Now, it depends on the value of K1 and K2, right, what will be the output. If the K1 you assume 1, this will be 1 and this will be 1. If you assume K2 equal to 0, this will be 0 and this will be 0, right, because both are 0. So, the output can distinguish the keys, right. So, for example, if I give K1 equal to 0, so this will be 0. If I give K2 equal to 0, this will be 0 and all are 0. So, output will be 0, right. If I give say K1 equal to 1 and K2 equal to 1, both will be 1 and output will be 1, right. So, the output will be 1. You got the idea? For the same input, for two different value of the key, my output is different. But in a circuit, if you give 0 0 0, output is one of them, right. It cannot be both, right, yes or no. So, in this circuit, in the original circuit, when there is no K1, K2, K3, the output would have been 0, because this is coming 0, this is 0, this is 0, this is OR of this. So, the output is 0. So, definitely this K1 and K2 is a wrong key, right. So, if you can identify an input which is distinguished input, just like 0 0 0, and if you just you can identify at least one of the key is wrong, right, you can discard one of the key as wrong, right, understood. So, this is an input, this is the input which I am interested in, and I will in a moment will show you it is not going to discard only one key, rather many wrong keys. Just here itself you see, if it is 0 0 0, in fact any cases where 0 1 1 0 and 1 1, all three will be discarded. Because if you give 0 0 0 1 or 1 0, one of the bit will be 1, and since it is a OR gate, one of the it will be always 1, and but your original output is 0. So, just giving this particular circuit 0 0 0, I would have removed all the wrong keys, and I have only 0 0 is the correct key, it will come out, right. So, this is what is distinguishing input. What SAT attack does? They try to figure it out this kind of inputs. So, I will formulate the SAT attack such a way, I will give you this circuit and I ask the SAT tool to give me a distinguishing input such that this is happening, right. If it can do that, with that I can discard many of the wrong keys, and it is not one of the wrong keys, at least one of the wrong key, but in practice it will reduce many of the wrong keys, and in quick time if I keep doing the same thing in few iteration, 3 iteration, 4 iteration, it will remove all of the wrong key and only correct key will remain, okay. And that is how we can get the correct key, right. So, I will explain how we will do that. Did you get the core idea of SAT attack? Yes. So, what should I do now? How do I do that? So, how can I model this problem as SAT attack, SAT problem, satisfiability problem, okay. So, let me explain here. So, as I mentioned, so I will just remove all this. Can I write this circuit as a formula? Yes, right, as a Boolean formula. Yes, right. So, it will be kind of AB XOR, maybe I will just use this as XOR. Let us say this is XOR. So, this is AB XOR K1, right, or BC, right, or AC, right, AC XOR K2, that is all, right. So, this is your formula, this is the formula of the circuit, understood. So, I can, given a netlist, I can write as a Boolean formula, agreed. So, the same concept that I talked about in the first half regarding the model checking of this information leakage, so I will take the same idea. I will take the original circuit formula, this is F. So, now this is my circuit as a formula, right. This is the same F, but what I will do? I will keep the input X as same. So, this is my input to the design, and key I created 2 copies, right. I created 2 copies. So, basically if you think about this formula was C, actual circuit was C, it has K input, X out inputs, and Y is the output, right. This is the key, this is input, this is output. I will create 2 copies, one copy is C K1 X Y1, and I will create another copy which is C K2 X and Y2. So, I just keep X as same, right, and I rename all the key with underscore 1 in this circuit, all the key here with underscore 2 in this circuit, and all the output as underscore 1 here and underscore 2 here. So, that is all, right. So, the same formula if you see here. So, I will keep the formula as it is. So, I will make it K11, K21, and another formula I will make it K12 and K22. Rest of the things will be same, right. Your output is say F. So, I will make it F1 and F2. You got the idea of this? So, this is my formula now, right. I will check if this is one formula, this is another formula, and your output is Y1 and Y2, they are not same, right. So, this is my Boolean formula now, right. This is my actual formula now. If I give this to SAT solver, and ask him to generate one input for which this formula is satisfiable. So, what it will do? It will give you some value of x, some value of k 1 and k 2, and it will tell that for this input, for this k 1 and k 2, your output is not same, and that is what your DIP, right. What is the definition of DIP? If you give some input for which there are two key values for which output is not equal, right. This is what I talked about in DIP, that there is an input for which two different key values for which output is different, right. So, I will not do in a simulation, but I will construct the formula corresponding to the circuit just like this. Everybody understand this? Understood? So, this formula is a Boolean formula, and search solver can do give you any formula, it will just say whether it is a satisfiable or not satisfiable. So, if you tell it is satisfiable, what it will return? It will return this input x, it will return k 1 and k 2, and it will tell that for this x, for this k 1 and k 2, because you have also put y 1 not equal to y 2 in the formula, output will be different. You got the idea? So, this is what SAT attack does, right. So, once it runs once, it will give you an input for which you can distinguish few keys. Okay. Everybody agree with this? I will come back to this. So, what will happen? So, this is what I am doing now. You find the distinguishing input by SAT attack. Then what I will do now is interesting. I got an one input now, right, and I have the oracle. I will give that value to the oracle. What I will get? What is the oracle? Is the functional IP, right. So, if I give this input, so I will get one input from here, right. If I give this input to the oracle, what will happen? It will give me the what is the correct output. So, I will get the corresponding to the correct output. Okay. What I will do now? So, this is what I am doing here. I will give this input to this oracle and I will get the output. So, what I will do now is this. So, I have this formula where I know the value of x, right, some 1 0 0 0 and all, and also I know what is the correct output. Okay. So, what I will do now in this formula, I will replace this a b, because I got the value of a b, right. So, a b is 0, c is 0. So, suppose it is return you this is DIP. So, in this formula I will put the value of a b and b c everything, and I know what is the correct output 0, right. So, I will modify these formulas by putting those values. What does it effectively means? It effectively means you are adding constant to this. So, for example, if you come here, if you put everything 0, this become k 1, right. It is basically it is saying k 1 1 equal to 0, because your output is 0 corresponding to this, right. If you put a c all 0 here, it will effectively this formula will reduce to k 2 1 equal to 0. So, that means you are basically adding constant to the keys, that your key cannot be other than 0, right. So, this is what effectively is being done, and those formula is getting added to the overall formula. Earlier the formula was this, with this I will now add this extra formula, whatever I got. Did you get my point? So, this was saying that your DIP should be this, now it is saying that your k 1 should be 0, k 2 should be 0, which is effectively tell you that you have only one value remaining, right. So, this is simple example, in one round it will solve it, but in practice what will happen? After adding this formula, I will again ask SAT solver, you give me one more DIP, right. So, it will basically I ask for this, can you give me one more DIP? If there is one DIP exists, so I will go back and I do the same process. If no DIP exists, what does it mean? There is no other DIP that can distinguish the keys, that means whatever the key remaining now are the correct keys. So, you will get the keys, right. So, if this is the all possible key value, after one DIP probably you are going to remove all these wrong keys, right. After next iteration you basically discard another set of wrong keys. Okay. So, basically previously you are discarding this part, after adding this you are basically discarding this part, right. If you do another round, probably discarding this part, and finally, when you go down, so only the correct key will remain here, and that will be your correct keys. So, this is what SAT attack does without giving any test case, right. It is mathematically only identify the DIPs, and Praveen will show you a demo now with an example that for a reasonably big circuit we can get the key into 3 iterations. Okay. So, just to illustrate what is happening here. So, suppose this is one DIP, right. So, suppose this is BDD, no need to go into the structure of the circuit, but say this is say variable A, right, A equal to 0, B equal to 0, B A equal to 1, B equal to 1, C equal to 1, D equal to 1 and E equal to 1. So, you come to this node and it says that these are the keys. Okay. So, there are 5 keys and 5 inputs in this design. So, there are many of the key values, right. So, suppose for this 1 1 1 output is 1. Okay. So, this is the correct output. What will happen? It will basically create 2 sets, right. So, all the path from this node to go to 0 are the wrong keys. Okay. All the path from this node going to node 1 is the correct possible correct keys. Okay. So, you can see how many paths are going 1, sorry, not this one. So, this is going to this, right. So, this is basically 1 1 1 0. So, this is one of the key value which is wrong definitely. You can see that there are many other, right. So, if you want this is also going, right. So, this is another possible key. So, once you do this DIP business, what is happening effectively, if you will go to one of such node and you will see that a subset of keys that will go to the wrong keys and set of the key goes to correct keys. So, all the key that is going to the wrong key is basically going to be eliminated. Okay. And all the keys that possible correct key will be written, right. So, this is the kind of core idea of SAT attack. Okay. So, so this is the overall attack. So, if you see here, so you create the initial formula where this is the formula I already talked about, then you check satisfactory for this, that formula plus y 1 not equal to y 2, you will get a SAT assignment. If it is SAT, you evaluate the oracle, you will get the corresponding correct output and you put this value into this formula, right. So, you are putting this k 1 and k 2, you are putting this x, you are putting y, you will get a formula on key and you keep doing it, and then once this while loops ends, you will get the SAT. Okay. So, so this is the basic idea. So, now I will request Praveen to show you a demo that how things works, right. So, he has implemented this idea, and just to motivate you that this is not something theory, right, it is happening for practical designs. So, for a small design he will show you the demo now. So, he has implemented this attack and he will show you.
Okay, hello all. Now we will see with an example that how SRI explained that DIPs will be able to prune out a class of wrong keys, not just 1 or 2. So, here is an example original circuit. It has 5 primary inputs and this is the logged version of the circuit, which is, as you can see, have 5 boolean keys, and this locking is basically your random logic locking, just for an example we have taken. And I have also shown the correct key for this circuit. You can remember it, it is 0 1 0 1 0.
So, remember the attacker has this circuit, but you do not have this, right. So, you can only run this circuit to get the output, but he does not know the internal of this.
So, we have already implemented the SAT attack, and I will show
the mic is not. You can show the code little bit what, so same analogy you are doing, right. So, just to.
So, I will just go through the code once. So, I will highlight and explain you what are the components that how we have applied the SAT attack in this code. So, this function is basically the executable, right. So, you can just map the executable that you do during a C program, that is a.out executable. It basically acts as the oracle. You give any input to an executable, it will give the output, right. So it is the oracle here. Followed by it, these are the two key values that we need for the mitre circuit. This is K1 and K2 instances of it. This is the, and then followed by the primary inputs and outputs of the locked circuit. And this is the solver that we are calling. You can use many solvers. There are crypto minisat solver, SMT solvers, and many other solvers that you can use to implement the SAT attack. I think, yeah, sure.
Is it visible now?
So yeah, and this is the lock circuit that the attacker has basically upon reverse engineering. So
This is basically representing the diagram, right? So all this AND gate, NOT gate, XOR gates and all. Yeah.
now, and this is the mitre. So we have
Mitre is the two copy thing, right? I do not use the term mitre. It's basically the first copy. If you see here, so in that design you have, I think it should work. You have this, right? So you have this ABCD is the actual input, right? So I do not create a two copy. I keep the same values. And for key, you have the K1, K2, K3 was the key, right? So he was creating that K1 underscore 1, K1 underscore 2. So the one is, this one is basically the first copy, and this is the second copy, right? So this 1, 2, 3, 4, 5 is the key value, and this K1, K1, K1 is for copy 1, and K2, 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 K2 is the copy 2. It's basically exactly what I talked about, right? And the output was Y, so he has created Y1 and Y2.
right. So going ahead, this is the main loop of the SAT attack. So initially in the while loop we check and till we check we have the DIPs or not. So this means Y1 is not equal to Y2. So this condition will only be satisfied when we have two different key values, and then we go inside the while loop. Upon checking the satisfiability, the important things are this. So IA means the current input the SAT solver has given we have a satisfying assignment for Y1 not equal to Y2. So this is stored in the IA variable, and we will print this and show in the terminal what are the DIPs that in each iteration that the solver produces. Then we print and see what are the two different key values that the SAT solver has simulated for satisfying this Y1 not equal to Y2. And then the most important part is these two statements. Here what we are doing is we are adding the circuit equation now only in terms of keys, that is two different key values, and substituting the same input which is the DIP, and along with that we are substituting the oracle value which is OA, and this OA is coming from the C executable function that I mentioned at the start, which is the oracle output.
Yeah, so just to again go up a little bit. So your actual formula was this two, right? So go up. So this was the actual formula, right? So you are replacing basically this find output, go off. This find out is nothing but this function, okay? So this is the find output function. So in this formula, this is basically a formula, right? So in this formula, go down. We are replacing this K1, K5 with these values. Basically I'm creating two copies, right? And ABCD is same. So effectively I have this two copy of this with one with this K11 and one is with K2. Go down. So once we get these values, right, this ABC from this DIP, go down. So he is replacing those values, right? ABCD he is putting the value and keep the variable as it is. So you have a basically a formula over K1, K2, K3, K5 with ABCD. Now you are if you putting the value of ABCD, what will happen? It will be a formula of K1, K2, K3, 5, right? And your output is also you get it from Oracle. So basically this is nothing but you are probably now saying this K1 plus K2 plus K3 plus K5 is 2, something like this, right? You are just saying that earlier you have the entire circuit where K1, K2 can have all 32 possible values, but you are saying that now K1, K2, K3, K4, K5 can have summation is 2. That means only those possible values true for which the total that has two ones basically, right? So you are excluding rest of the conditions. So this is adding, and its push means basically adding to the formula, and then again is calling the same thing, right? This is exactly the same SAT attack I explained. So you can run now and so.
Is it visible? Okay. It will go up. One second. So yeah, so we have already run the attack. So as you can see, we have for each iteration the DIPs, its corresponding oracle value and the two different key values are being printed in the terminal. So in total we have 6 iterations for the SAT attack. Subsequently we will show how each DIP now is able to prune out more than one keys using the BDD data structure.
Just to add now, so there are 5 keys, right? So 2 to the power 5 is 32. So there are 32 possible keys, but we are not running 32 times, right? So we are turning maximum 6 times. And the number of iteration depends on where you have locked, okay? So in first iteration the DIP is 1100 and oracle output is 1. So it basically, this is K1. So this is basically saying that 10101, right? And this is 00100. This is the 2 key values. And then the next iteration DIP is this and oracle is this. So this is how it's happening. And finally go down. In the last iteration it will say that no DIP and it will basically give you the correct key value.
Yeah,
so the correct key value is 01010. You remember that was the correct key, right? So without running any test case or anything, just writing that code, running how many times? You just run it, you just run one more time. It just comes seconds, right? Couple of seconds it will what happen?
the server gets disconnected once.
Okay. Just couple of seconds, right? So you give the key to you. Yeah, so you can go to the.
So now we'll continue with the build. Yeah.
You get the idea, right? What is happening? So we have developed certain the SAT attack versions. The basic version, if you take the entire circuit, you can go up to say 100 keys, 200 keys. You can break up to 200 keys in a circuit within minutes, right? Then there was a computation in which they have given a circuit which has 5,000, 4,000 number of keys, even 15,000 keys. Okay, so there obviously you cannot break with the entire circuit together. So we are basically applying that attack incrementally, a part of the circuits. Okay, with that we have shown that even we are able to break circuits which has 5,000, 6,000 keys. Okay, so that's not safe as well, right? But background we are using SAT attack, but not for the entire circuit, partial circuits. So you have one PPT, right? The same diagram, right? That's all. That I have shown, right? So what you are supposed to see is this one. So this is the diagram corresponding to the design he has taken, right? So it has A, B, C, D is the input and K1, K2, K3 is the output, right? So what was happening there is this, right? So whenever you get one of the DIP, let's say suppose this is your DIP, right? So you are coming to this, say this one, which is 1 0 0 0, right? So this is your DIP. If something is missing, it can be anything, right? You can take 0. So for this, say output is say 1. You will see the paths that goes to 0 are the wrong keys. So it will effectively remove all the keys that goes to the wrong output, because for this input you know what is the correct output, and let's say the output is 1. This is your correct output. So all paths going to this can be correct key. You don't know, one of them may be correct key, but definitely that goes to the wrong output is wrong. We are going to discard. So this is how this SAT attack is so powerful. It discards a subset of wrong keys, not one wrong key. If it is discard only one wrong key, it would have been done, right? Okay. So, I will now move on to the last part of today's talk. So, this part I will talk about how machine learning can help you identify the correct keys. Okay. So, that is something is interesting, right. So, in couple of years, last couple of years, people try to use machine learning based attacks on the lock design. Okay. So, that is something I will go through what couple of works are there. So, so this is oracle less attack, that means it is a passive attack, you do not have the functional oracle, you just analyze the circuit and try to guess what is the correct key. But since you do not know the oracle, the accuracy of the key may not be always 100%, you may get 70% of the key correctly, right. But that is also good enough, because if you have 100 keys, if you get 70-75 keys from ML, rest you can do some other techniques, right. So, this ML technique can be combined with any other technique like SAT attack to break a bigger circuits. Okay. So, what is basically is happening is this I have already discussed, that if you have original circuit, you apply random logic locking and then you do resynthesis, which will make some impact, right. So, resynthesis is kind of your XOR become XNOR, XNOR become XOR and so on, right, and some of the gates might change little bit, right. This NAND gate become NOR gate, and this is basically because of bubble pushing and all, and your resynthesis can also make some modification. Resynthesis is basically the logic synthesis tool. So, logic synthesis also apply many optimization, so they can make some modification, and you have only this design with you, right, nothing else, right. Here you know what are the key inputs and what are the actual input, and you do not have the oracle with you, and your objective is to use machine learning technique that will guess the correct key values. Okay. That is the kind of idea. So, the basic philosophy of this ML based attack is that if you do this, you have say design, right. So, you got the lock design, what they will do, they will now again relock, right. So, they can lock again with some keys, and then this do this circuit synthesis, and then they will see what are the structural changes happening, right. So, if it was pre synthesis, after modification this was happening, if this is the pre synthesis circuit, if it is this is the post synthesis one. So, the modification is happening to this, because he knows the circuit, he know what is the where he has locked and what is happening around that, right. So, he will keep this as a training data set, right. So, it basically say that if this is the pre synthesis circuit, if the key value is 0, after modification this will be the modified circuit, right. So, this way you can create the training data set for ML model, right, and the main success is happening because this modification is local, right. So, you are adding only one key gate, and even if you do bubble pushing, that will only impact maybe this gate, this input, or maybe something around this, right, and maybe one level or two level. So, you can create all those pattern, right. So, if this is the substructure, if you make this modification, this will be the positive outcome, and so this is the post synthesis structure, and that is the correct key. So, you can create the training data set and you can train an ML model, right. So, then in your lock design, you now identify those pattern and you query that model now, right. For this structure, what was the correct key, right, what was the pre synthesis structure, it is possible, right. Did you get the core idea? So, this is the first ML attack was happening in 2021, where they try to see the local changes, create the data set, based on that they train the ML model, and then they predict in the entire design, because you know what are the key gates. So, you identify a maybe parameter of 2, length 1, length 2, all these sub circuits, and from there you try to predict this one, right, what was the pre synthesis circuit or what was the key value. You get the idea, right. So, this was the first ML based attack happening. So, this is basically the idea that you lock the design defender, and then what they do, they will basically relocked, resynthesized, and then you create the data set. This is the training phase, and then they will use this for inference. Okay. So, this was the kind of idea, and they effectively use GNN, graph neural network. So, this is very well known for circuit representations, and they keep all the key gate types and all those information in that. So, I am not going into that detail, but the key idea is that you store the information in GNN. Okay. So, now so this whenever this one came, this is specifically targeting the XOR based locking, right. So, immediately if you apply the same model, the trained model on marks based locking, that won't work, right. So, the immediate remedy is that do not use XOR based, you use the marks based locking that I have already talked about. But that is obviously you can also train another ML model for mark structure, because the structure because in MART will be another similar thing, right. It is not out of box, it will be something very similar. So, that is happening, that you now basically see you put marks and you try to do that thing, and you can actually identify the gates, right. So, the attack that was proposed in 2022, they basically come up with a nice idea that you create a marks based locking, your original circuit, suppose this was connected, right, this was actually connected to here. So, you put a marks here and you can't connect this one as the false one, right. So, if you predict it correctly, there will be a create connection, this is the correct circuit, right. But if you predict the key value wrongly, there is a dangling, right. So, this gate is become dead, right. So, the output is never getting used. So, what they will do, they will basically train the model and predict and check whether you are reaching this or that. If you are reaching that, that means this is wrong key, right. So, you cannot have a dangling, because your original circuit there cannot have any gate which is hanging, right. So, they will basically say, oh, this must be true just to make the circuit works. Okay. So, that is the deceptive logic locking for hardware integrity protection against machine learning attack. Then you have this. So, this was the basically marks attack, right. So, you can actually think about the MN can learn the graph representation and basically the around key control marks, which is very similar to the previous attack. Then these guys talked about that what I will do, I will basically not create this kind of structure, rather I will create a marks which will connect from two existing circuit values, right. So, there is no hanging thing. Okay. So, what will happen, this demarks is basically even if you predict this 0, so there will be a connection, if you predict the value 1, then there will be also connection. So, there is no dangling kind of thing. So, you will decept that kind of attack, right. So, what so this is a good solution against the attack it is talked about here, that you basically decept the marks based predictions, the ML which can make the connections, I mean which can predict the connections. But then the next attack comes in 2022, which is called marks link attack, which is basically try to do the link prediction. Okay. So, the basic idea here is that you have this circuit, right. You have either this link is there or this link is there, this link is there or this link is there. So, there are those 4 possibilities, right. And the philosophy of this kind of attacks, that in your entire design you can have 20 adders, right. You probably you probably lock one of the adder, right. So, other adder you may not have locked. Okay. So, the repetitive structures is available in your entire design, and you try to identify other structure, you learn the other valid structure with the part of the circuit where there is no locked, where the locking has not been done, right. And those are the valid structure, and based on those, suppose you have basically learned an adder structure, and this is basically locking around the adder structure. Now, you see which of the link actually relate this circuit to adder, right. So, you basically see whether this, if I predict this link is the connection, is it close to the another pattern which is available in your design, which is an adder, or this is doing that. So, one of them will do, right, not both of them. So, based on that you can actually see the whether which link is more viable, right. You basically give a score to each link, right. So, this link is 1, this is 0.4, this is 0.8, this is 0.9. So, based on that you decide which link to be selected, right. So, it is basically called link prediction attack, where you try to predict the possible links, the score for possible links based on the other structure of the circuit and which is matching to existing structure, right. And it is very common in hardware, because your circuit not everything is different, right. You probably have lot of multiplexers, lot of adders, lot of multipliers. So, similar things is available in the entire design. So, if you lock probably an adder, there will be another 30 adder in your design, through which I can learn what is the possible structure, and based on that I can predict which link actually very close to that, right, and based on that you can identify the key, right. So, that is the kind of idea of this. Any question on this? You got the idea, right. So, these are the very few works, but I would say this basically try to attack the circuits which is preset errors, right. All these marks based locking, XOR based locking, these are all preset areas, but the value of this kind of attack is that they do not use the oracle. If you argue that this particular circuit has not come into the market yet, then this attack is not possible, all the SAT based attack is not possible, because they use the oracle, right. Whereas, here without oracle also you are doing things, okay. But still this machine learning based attacks are still pre-SAT era, okay, which I did not talk here in more detail. Is post-SAT, there are many locking technique come like SAR lock, you have SFLL, okay, strip functionality logic locking. So, those are very strong protection technique, which make sure that even SAT attack cannot break them, okay. So, this ML attack usually targets the locking which is pre-SAT era, which is already broken by SAT attack, but they try to see the value because they are not using the oracle. So, in long run we should have even ML attack for post-SAT eras techniques, right, or you can actually think about that finally, your objective is to create a locking which is agonistic, or it is basically give protection against all kind of attacks, right, whether it is a formal attack like SAT, whether it is a ML based attacks. So, you should kind of develop a locking strategy which can give protection against all of such attacks. And one of the key idea which I feel is you cannot just use one of the type, right. You cannot just lock the circuit with XORs, right. You use some XOR, some marks, then none of the techniques will work, right. It will mix everything, this ML based techniques, or you use some of the post SAT also, right. So, you basically have a circuit which you 20% use XOR, 20% say marks based locking, 20% maybe post SAT, maybe SFLL, and not only combinational part, right. You have also sequential part. So, I have not talked about sequential locking here, right. In sequential part is basically you have a FSM, you try to lock your FSM. You use some of the FSM based locking there. So, if you use 20 rules for 5 different technique, you combine everything, right. So, now none of the technique individually will work, right, and most importantly you do not know which key is being used for which kind of locking, right. So, this will make the lock design much more robust, and in my understanding the kind of existing techniques so far in what is developed in last 2015 to 2025, in 10 years, none of them will be able to break your circuit if you combine everything, right. FSM locking, sequential locking, pre-SAT locking, post-SAT locking, you combine everything together and you make a circuit with all of them. So, then that will be real protection, and that I think is the way ahead. Okay. So, this is a very active research domain in my group also, this Provin specifically working on this, and there are a lot of other research group worldwide, they work on this, and idea is that how do you come up with a strong logic locking scheme with low overhead and high security guarantee, right. And if you are interested, you can dig into further. Okay. Thank you. So, with this we close today.